Okay. Hello, everyone. So welcome back to this course on topological recursion. So as I pointed out last time, lecture notes are available on the archive, so feel free to use that as a complementary material. So as we discussed on Monday, yesterday, what we'll talk about today is we'll go back to the definition of Airy structures and the main theorem due to conservation Salam. So I'll just sketch a proof, and then we'll do some examples, and then we'll move on to topological recursion as originally defined by Hénard and Arantin. All right, so let me just remind you to start with what we ended the lecture with yesterday. So remember, we started with Witten's conjecture, talked about how it relates geometry, integrability, algebra, and also topological recursion. And then we saw that we can, starting from the point of view of algebra or Virasoro constraints, we can define a vast generalization of differential constraints such that they always have a unique solution in the form of a partition function. Okay, so this was the idea of Airy structures. So I'll just remind you here of the definition and the main theorem, and then we'll sketch a proof. Sounds good? So what was the definition? So the way I presented it, so we have a left ideal in the Ries-Val algebra. Remember, this is the Val algebra, but with an auxiliary parameter h bar, which makes it a graded algebra. Now we say that it is an Airy ideal or Airy structure. So I'm going to write Airy structure here, as it's usually called. If two conditions are satisfied, so there exists a bounded generating set. So this is a set of generators for the ideal. So there's one for each variable or each index in my index set, such that two conditions are satisfied. So each of those starts with a derivative plus higher order terms in h bar. And the second condition, which is a condition on the ideal itself, is this condition, which, as I argued last time, is a very non-trivial condition, but is a necessary condition for the ideal to be the annihilator ideal of a partition function. Okay, so this is the definition of an Airy structure. Very simple. And the main reason why this is interesting, as I ended the lecture with, is the main theorem in this area, which is due to Kontsevich and Subelman, which is the following. So if you start with an Airy structure, so let I be an Airy ideal or Airy structure, then the statement is that then there exists a unique partition function z. So remember, a partition function for us is an exponential of a generating series of basically an phase sum in h bar with polynomial coefficients, such that it is killed by I. So the annihilator ideal of the partition function in the Ries-Val algebra is the Airy ideal I. Okay, so this is the main theorem. And the reason, as I said, that it's interesting is the following. So basically, the statement here is that I kills Z. So equivalently, HA kills Z for all A in the index set. And the reason that it's interesting is that not only does it kill Z, but Z is the unique solution, so it uniquely fixes it. So the recursion relation that we get, as we will see, we can write them down very explicitly. So these recursion relations uniquely fix or uniquely reconstruct the partition function Z. So it provides a complete solution to the theory if Z is, of course, an interesting object. So if it calculates something interesting, that gives you a way of completely reconstructing or calculating the coefficients, the FGS, the coefficients in your partition function. Great. So this is the very important result, but the proof is actually not too complicated. So I'll present a sketch of the proof just to give you an idea of how it goes. And the way I will present it is formulated, as I mentioned before, in a paper of mine. So let me write the reference here. Paper of mine, B, and Thomas Kreutzig, and my former students, Aniket Joshi, in whatever, I think 2022. And it's equivalent to the proof that was originally formulated by Conservative Subliman, just written in a different way. All right, so let's move to the next slide. So I'm writing proof here, but it really is just a sketch, of course, because that would be way too long for a lecture. But the idea here is the following. So the key thing is that you want to work in the H-bar addict completion. So that sounds very fancy, but it's not. So what this means is just that in the Riesz-Val algebra, remember the elements of your Riesz-Val algebra are polynomials in H-bars, in H-bar whose coefficients are differential operators, with the degree of the operator bounded by the degree in H-bar. Now here we want to allow infinite sums in H-bar. That's what H-bar addict completion means here. So that's formally what you would write is that you write that as a product instead of a direct sum of the subspaces in the Bernstein filtration. But really, this is just fancy notation to mean that you just want to allow infinite sums in H-bar, not just polynomial in H-bar. Okay, and the point here is that, so let me write that just to make it clear. So we allow infinite sums in H-bar with the same constraints that the coefficients are differential operators in these subspaces of the Bernstein filtration. Now, the reason that this is important is that the ideal here that we start with, the Airy ideal, which is in the Riesz-Val algebra, well, out of this you can construct an ideal in the completed Riesz-Val algebra, because all you do is you take the same generating set, but now you multiply on the left by possibly infinite sums. And it turns out that this ideal hi-hat is like a, sorry, I play drums, so hi-hat is more natural to say than I-hat. Sorry. But I-hat is the ideal in the completed Riesz-Val algebra, and it turns out that this ideal is actually quite simple. So even though I is not, I-hat is very simple, and that's the key to the proof. Okay, so the proof actually goes in 4 steps, I would say. So the way at least we proved it. So the first step is the following. So this is where the recursive idea comes in. So the first step is to show that there exists a set of differential operators that we'll call capital H bar, not to be confused with H bar, the parameters. I don't know why we used capital H bar as a notation in that paper, because that's very confusing. When you say H bar, it means 2 things. But that's what it is. So I'm going to stick with our notation. So yeah, so we show that there exists such a sequence or collection of operators in the completion here of the following form. So these are much simpler than the h's that we start with. So these start with the derivative, just like the h's, but then you have an infinite sum of terms, potentially infinite. It could be finite, but it's usually infinite, where the coefficients are just polynomial in the variables. Okay, so this is much simpler, because if you remember, the HA were also starting with a derivative, but the higher order terms here could be anything. So they could certainly include derivatives. I mean, they generally do. But what we show here is that there exists such a collection of operators where the higher order terms are just polynomial. But it's very important that is only true in the completion. Right? These are infinite sums in H bar. Okay, and the way you show that is actually very simple. This is just a recursive construction. So you start with the HA, right, which looks like this. Now you go to the next order. So you're going to get H bar squared, then you get 2 types of terms. You get a term that is just polynomial in the x's, and you get some terms that have a derivative on the right. Now, take the derivative, you can replace H bar del you can replace by, so I'm just being schematic here. Of course, del would have an index, but I'm just being very schematic here. You can replace H bar del by H minus something of higher order, right? By the definition of the H's. So you can replace the terms with a derivative on the right by terms with an H on the right plus higher order terms. And terms with an H on the right are in the ideal by definition of the ideal, because it's generated by H. So ultimately, what you end up with when you do this recursive process is that you end up with the statement that you get something h squared polynomial plus something in the ideal plus higher order terms, but then you keep going. At the next term, h cubed, you do the same thing. You get poly plus something ideal, and you keep going. And because you work in the completion, you can keep going forever, right? That's the key. If you were not in the completion, that process wouldn't close, wouldn't end, so you would be in trouble. But in the completion, you can keep going forever. So you end up with an operator that is basically just a derivative plus the sum of polynomial terms plus something in the ideal. So you can construct these operators here, h bar a, as being just the polynomial part, right? And it's also in the ideal because you just subtract something from the ideal. Okay, so it's a recursive reconstructions. Maybe it's not clear here because I'm being pretty quick, but as one of the key ideas of the proof is you construct this collection of operators are much simpler, which are in the ideal I hat. Okay, so that's the first part of the proof. Now the second part of the proof is actually fairly simple. So this is just to show that this collection of operators we constructed actually generates the ideal I hat. Not only are they in the ideal, they also generate the ideal. So you can write everything in I hat as something acting on the left of some combination of h bar a. Okay, so that part is quite simple. It's just again a recursive process. It's very similar to part one. Now the third part of the proof is where the ideal condition comes in. So far in the proof, all we've used in the definition of Airy ideal is the first condition. We just used the fact that the h's start with a derivative. That's all we've used. We haven't used the condition on the commutator of the ideal with itself. So that comes in part three. And part three is the statement that you can prove that these operators h bar a actually commute. They are commuting operators. So this is a complete commuting collection of operators that generate your ideal, which is, if you've done some quantum mechanics, this is very similar to when you construct these observables that commute in quantum mechanics. So this is kind of a similar idea here. You get a complete set of commuting differential operators in your ideal that generate the ideal I hat. That would not be true in I, but is true in the completion. And that's almost the end of the proof, because the fourth step in the proof is just a use of Poincaré's lemma, which you may know from differential geometry, which is about one forms that are closed but not exact, or when are they, if they are closed and exact, and so on. So this is the statement here that you use is just formulated in terms of differential operators, but it's the same statement here. The fact that these h bars commute implies that these polynomials PA that I had in my definition of h bar a, so these were polynomials of degree n, are actually all derivatives of the same polynomial of degree n plus 1. So that should be a capital A. Okay, so that's probably not clear at all to most of you why this is an application of Poincaré's lemma. And again, I don't want to get into the details of the proof. This is just basically a technical, well, it's just an application of Poincaré's lemma. That's really what it is. But you can take my word for it. If you know that these h bar commute, you just take the form of the h bar that we calculated. The fact that they commute tells you that the derivatives of the PAs the mixed derivatives have to kind of, well, del BPA is equal to del APB, and that's just the same as taking the differential or the exterior derivative of one form. So you end up with Poincaré's lemma. Did I say it right? Okay. Anyway, that is an application of Poincaré's lemma, and that's basically the end of the proof. So why? Let me now conclude the proof. So what have we shown? So what we have shown is that this ideal I hat is generated by a collection of operator h bar a, which take the form derivative plus or minus, I introduced a minus by convention here, minus sum h bar to the n del a q n plus 1. And that basically tells you, with just using the simple application of derivatives to exponentials, that is clear that if you act with these on the z, which is just the exponential of this sum that we have on the right here without the del's. If you act with a derivative and you subtract the derivative of the argument of the exponential, then of course you get 0, right? So that's clear. So what you've shown here is that z is annihilated by the ideal I hat. In fact, you have shown a little more here, but that would have to be argued. What you've shown is that I hat is the annihilator of z in the completion, and then you have to argue that this also implies that I, the ideal, not in the completion, but in the not completed algebra, is the annihilator of z, which was what you were trying to prove. Okay, so the main point here is that you want to work in the h-bar completion so that you can deal with infinite sums. And in this completion, the ideal is very simple. And the two conditions become clear. So the first condition in the definition of Airy ideal, which is this condition 1 here, is required for this recursive construction of these operators h-bar that live in the ideal. And the second condition is essential to show that these h-bar operators commute, which is what gives you what gives you the result that they actually kill a partition function z. Okay, so hopefully it makes sense. This is pretty heavy stuff for the beginning of a lecture, but if you are interested in the details of the proof, I guess in my lecture notes, I also only sketch the proof. I sketch a bit more detail than this, but I just give a sketch. But the details are all in the paper with that I referred to. And yeah, so a good question here is, that's a very good point. I didn't really understand why the solution is unique. I did not actually mention why it is unique. So, but the point here is the following. When you do this reconstruction, so what can you see my cursor, by the way, when I do that?
Yes.
Yes, okay, good. That's good, so I can point. So when I do this reconstruction of the capital H bar here, this is uniquely defined. So the polynomial part is uniquely defined here when I do the reconstruction. And then, so these operators H bar here, the polynomial part is uniquely defined. And then when we use Poincaré's lemma, the Q's are uniquely defined up to constant terms, because of course we take a derivative here, so we could change constant terms. But when we say that the partition function is unique, we always mean unique once you fix the constant term to be 0. So here we define the Q's such that evaluated at 0, they're 0. And once you have that, you can think of that as initial conditions if you want. Once you have that, then it's uniquely defined by the recursive process here. Okay. But again, if you want to make sure, you'd have to, I mean, this recursive process, step 1 is the key one here, and you'd have to do it carefully. So you probably want to look at the paper where we do it in a much more explicit way, or you can do it yourself, and then you'll see that it uniquely defines the partition function.
I had a quick question.
Yes.
So are we working in the completion because of the third point to show that these operators commute? Was it the reason why we started working in the completion?
Well, good question. So I mean, in first point, right? Because the capital H bar wouldn't live in the Riesval algebra. These are infinite sums. Right, so this recursive process at every step of the way, what you do, so you start with the order degree H bar square. You have polynomial terms, you have terms with derivatives on the right. So you replace the derivatives by H up to higher degree terms. So you replace it by something. So in other words, the terms with a derivative, you can replace it by an object that lives in the ideal plus higher order or higher degree. But of course, if you were working not in the completion, then at some point, because you cannot have infinite sums in H bar, at some point you wouldn't be able to keep going because you always need to change the terms of higher degree. So you'd have to stop at some point to get a polynomial in H bar, and then you would end up with something that is not polynomial at that degree.
Yeah, but what I was wondering is that did we kind of wanted this operator to commute, and therefore we wanted, because this does not commute in if we are not in the completion, right?
Well, they're not, and they don't exist in the real
Yeah, but
life.
does the H bar, sorry, HA without the bar, do they commute in the
No,
res while?
no, exactly. These
Yeah, yeah.
H's don't commute. I mean, they could. If they do commute, of course, it's an Airy ideal, but it's a very simple one. So if they do commute, all of that is pretty much
So
useless.
in general, they don't commute.
Oh, exactly. In
Yeah.
general, they
That
don't.
was what I was wondering, that if we wanted it to commute, that makes like we work in the completion. And is that like basically I'm trying to understand the motivation why we started with the
Yeah.
completion.
I mean, it's good point. There are many ways you can think about it. One way is that once you work in the completion, you can find a generating set, which is a complete set of commuting operators. That's
Yeah,
one
okay.
way to think about it, which would not be true in the Riemann algebra.
Yeah, thank you.
Okay, good. So thank you for the questions. Now let's move on to do some examples, which hopefully will make the construction a little clearer. So the point here is that, of course, I've emphasized that before, but the main point I want to say here is that Airy ideals are cool. So that is important. Something that you should always keep in mind when you do math. You better do cool things, otherwise, it's boring. But what do I mean by cool here? So I've said that before. I'm not going to write it again. But if you have an Airy ideal, then you get recursion relations for the coefficients. So that's cool. Now, if it's great to come up with new definitions and new abstract nonsense, as people say, but if there are no interesting examples of the definition, it's pretty much useless, right? So the first thing you want to check is that there are some examples that are non-trivial. Okay, so let's do a bunch and see. In fact, there are many examples of Airy structures. So one thing you could do, by the way, maybe I'll write it down. So the first thing you may be tempted to do would be to look for examples with the index set being a finite set. So in other words, you only work with a finite number of variables. Now, this is interesting in its own because this is not related to topological recursion. So the usual topological recursion of N on Latin, as we'll see, corresponds to Airy ideals with over a set of variables that is countably infinite, always. So this would be a generalization. This would be a different kind of recursive structure. But and there's been some work on this. In fact, there's some sort of classification. So some examples of Airy ideals, as we'll see, come as representations of Lie algebras. Now you could say, well, let's classify what representations of Lie algebras take the form of Airy ideals or Airy structures. And there's been some work on this by a few people. So I'm not going to comment more on this. The point is that it's an interesting classification question. In fact, you can go beyond Lie algebras as well, because a lot of examples of Airy structures are not representations of Lie algebras. And it's an open classification question in that case for the finite index set. But all the examples that we know where the FGNs have interesting interpretation in physics or geometry are when A is infinite. So I'll focus on that for these lectures. But if you're interested, so if you look at the ABCO paper, this is called ABCD of topological recursion. So Anderson, Borel, Chekhov, and Arantin. And they have a partial classification of these finite case, and there was some other papers, I forget the authors, unfortunately, after that provided even more details on this. So that's somewhere you can look at this. Okay, so the first example that I'll talk about, so I said it's really interesting if you have a non-trivial example. So the first one I'll talk about is a trivial example. So as we often do in math, we start by doing the trivial examples just to show that, I don't know, we can be boring too. So let's do a trivial example. So the trivial example is if you take your operators that you start with to be just derivatives, right? Just don't add any higher degree. Well, okay, that's very simple. Then clearly, this is a case that corresponds to what you were saying. Swagata, I think that was you. Yeah. So if you look at these operators, they obviously commute, right? Derivatives commute. Whenever you have commuting operators, this condition for the ideal is satisfied. That's always true. In fact, if you don't believe me, you can show this. That's a good exercise. So you show that if the H's commute, then the left ideal generated by the H's satisfy this property. So that's great. And obviously they have the right form because they start with a derivative. So that is an example of an Airy ideal. Now, what is the partition function here? Well, it is pretty boring. This is the exponential of a series in x in the variables that is killed by all the derivatives in all the variables. So this is just the constant 1. So in other words, all the FGNs, the coefficients are 0. Any k, you'll get 0. Okay, so that is the trivial case. It's not very interesting. But okay, that's an example. Okay, but let's do something more fun. So the first example that is non-trivial, that is relevant, here we've already seen. So this is the Kontsevich-Witten example. So I started these lectures by giving you a very general kind of overview of Witten's conjecture and relations with Dijkgraaf-Verlinde-Verlinde's Virasoro constraints. Well, this is an example of an Airy structure. So you can think of Airy structures as a vast generalization of these Virasoro constraints. So how do you write this in the language that we developed? So we take our index set to be the odd natural numbers, so odd positive integers. Sorry, I'm having trouble writing. Okay, that's better. It looks a little weird. Let me put the L closer. Okay, odd natural numbers. And then I'm going to define, so the Virasoro operators that I had before, I wrote down in a while back, are these operators. The sum m plus n is equal to 2k, where m and n are odd. Normal ordering, meaning all the derivatives on the right. And this is for all k greater or equal to -1. Now, to fit within the language we've developed, we should define, just re-index these operators, right? So that we basically, k goes start on -1, so 2k plus 3 will run through all odd natural numbers here. So this is just a redefining of indices. That's not relevant. But then the key point, as we've said before, is that these form a representation of the Virasoro algebra. So again, you can show that. So you can show that if you commute any two of those, you'll get the Virasoro algebra, or rather the the subalgebra of the Virasoro algebra. So the central charge does not appear here. So that's for mn greater or equal to -1. Remember here that the j's, I didn't write it down, but remember that the j's are either derivatives or 0 or m time variable, depending on whether m is positive, 0, or negative. Okay, and the second thing you can show, this is a good exercise, is that you can show that these commutation relations here imply, again, that if you look at the ideal generated by those, it satisfies this condition. As we'll see, this is very general. Whenever you have a condition that the commutator of the generators is a linear combination of the generators. So in other words, that would be the case if you have a Lie algebra, which is the case here. Whenever you have a Lie algebra, then this will be satisfied with an h bar square here. Sorry, then this will be satisfied. Okay, so that's a simple calculation. So you can show that. So then clearly it is an Airy ideal because this condition is satisfied, and it starts with the derivative plus higher degree terms. And all the derivatives appear because our index set is odd natural numbers, and all the odd natural numbers appear here. So you do get the right form, get an Airy structure. So fantastic. So we conclude that I is an Airy structure or Airy ideal. What does that mean? Well, that tells us there's a unique partition function z such that it is killed by z, by the ideal I. And of course, we know what z is here because we've talked about before. Z is the tau function. So the Kontsevich-Witten tau function of KdV integrable system. It is a generating series for intersection numbers an MGN bar, and so on. All these nice things that we discussed before, these fit here. But the main point here is just that this is an example of an array structure. So that's great. That's I guess the first non-trivial example, and that's probably because I get this question a lot. Why is it called Airy structures? I can't read in Kontsevich and Subelman's minds, but I think this is the reason why it was called Airy structure, is that this example here. So how do you prove, how did Kontsevich prove Witten's conjecture here? So what he did is rewrite the partition function as a matrix integral, as a matrix model. And this was an interesting matrix model, which is basically a matrix generalization of the integral representations for the Airy function, right? And that he called the Airy matrix models. And I think that's probably where the Airy comes from in the name. Okay, so that is a cool example. But of course, if all we get is just the starting point within conjecture, that would be pretty boring again. But it turns out there are many, many more interesting examples. So the next example is a very small variation on the previous one, but it turns out to be quite interesting and very, very new in many ways. So what is the example here? So I take the same, no, sorry, not quite the same. Yeah, I think the same set, but not quite the same operators. The same set here is the odd natural numbers. But then I'm going to define my operators slightly differently. So there's still LK. The only difference in the LK is the leading term. So I take 2k plus 1 here instead of 2k plus 2. Okay, and that's it. Everything else is the same. So let me write it down again for completion, but it's all the same for completeness. Sorry. So this is all the same. And the other difference is that we only keep the non-negative k's. Remember, in the previous case, we started with -1. Here we start with 0. But we also change the leading term here. Now, again, this is something you can show, but it is not too hard to show that this is still a representation of the Virasoro algebra, just a different one. So it still satisfies this commutation relation. So that's now for m n greater or equal to 0. So that implies, by the same argument that you hopefully have proved if you did the previous exercise, I mean, you didn't do it now, obviously, because I said it 2 minutes ago, but if you do it, you will prove that. That implies that this condition is satisfied, and then that implies that I is an Airy ideal. Why? Well, of course, the condition on the ideal is satisfied, and the form of the operator is the right one, because now, again, it starts with derivatives, and because we start at 0, and this is now 2k plus 1, we go through all the odd natural numbers, so we do get, indeed, all the derivatives appearing as the leading term of all the generating set. Okay, so we get, again, same statement, there exists a unique Z such that it is killed by the Airy ideal. And then, of course, the question is, what is the Z? Now, is that an interesting thing? This is not, it looks very similar to the Virasoro constraints of Witten's conjecture, but are not the same. And in fact, they give rise to completely different geometry and completely different meaning for Z. So the cool stuff here, which I will not prove, but what you can prove and was done in recent work, is you can prove a number of statements. You can prove that Z is still a tau function, but it's a different tau function for KdV. So what this means is that it's, if you take the second derivative of the log of Z, you do get a solution for KdV, but a different solution. So it satisfies different initial condition. This is called the BGW tau function. So BGW here stands for Berezin, Gross, and Witten. So this was this comes from the matrix model. It's a tau function that was known a long time ago, but it arises here as the solution of these constraints. And the initial condition for those interested here is different. So if you take the second derivative of the log of Z, and then you set all the variables to 0. Oops, not what I meant. Set all the variables to 0 for all I greater or equal to 2. Then instead of having just x1, what you have is 1 over 8, x1 minus 1 squared. That's the initial condition. not relevant. We haven't talked much about KDV here, but this is different initial condition, and it turns out to be what you get here. By the way, also very interesting, it is certainly not true as far as I know that tau functions in general of KDV will satisfy differential constraints, Virasol constraints, differential constraints in the form of representations of Virasol algebra. But it is true for the Kontsevich-Witten and the BGW tau function. But I don't know how general this would be. So I think that's not very well understood. Okay, and the even more interesting is the enumerative geometric interpretation here. So remember these coefficients here for the partition function take a very nice form here. So if you write it down explicitly, again, you have this double factorial factor, and then you can rewrite it as an integral over the moduli space of curves. You still have your psi classes. So that's what you had for Kontsevich-Witten. Now the FGNs here are very different. So this is not what you have. What you have is something like this, but you have an extra class here, capital theta. And this kind of basically for every G and N, you have a cohomology class here. You can construct what these cohomology classes are very specifically. This was done by Paul Norbury in 2017, I think. Published in 2023. I think it was on the archive in 17 or 18. And these have been known as Norbury classes. So this is very recent. And what you can show here is that these cohomology classes exist. First, they're very nice. They form what is called a cohomological field theory, but a special one where something called the unit axiom is actually modified in your cohomological field theory. And in this case, Z becomes the descendant potential of this cohomological field theory. So this is all very fun stuff that is all like very rich stuff that fills the corner of this square, you know, the geometry, integrability, all these corners of the square for this example, which is, one could say, a very, very minor variation on the original example of Kontsevich-Witten. So already, like the formalism of every structure gives rise to some very fun stuff in this case. Okay, so if you are interested in all of this, again, we will talk more about this when we talk about topological recursion, well, a little bit more about this, not much, but there's more in the lecture notes. Okay, let me give you more examples. So the next example is actually a vast generalization of these two. Okay, so what you could say now, so if you look back at these two examples, they both have a nice property. Well, they're both representations of Virasol algebra. So now we're going to get beyond this. So we're not talking about Virasol anymore. But both of these examples are degree 2 in H bar, right? So they only have a term of degree 2 in H bar and nothing of higher degree. So you could ask, well, let's just pick a very general differential operator of degree 2. What happens? Okay, so this is the next example. So let me now take any index set. So A is any index set. And let's define very generally operators that have only the appropriate leading term in H bar and then H bar squared terms. So here I'm going to use the notation, the standard physics convention that I sum over repeated indices. Otherwise, I'd have to write a lot of sums. So hope that's okay for all of you. So if I write down a general operator of degree 2, I'm also imposing here. Well, let me write it down first, and then I'll say what I'm imposing. I'm imposing a constraint here that I don't have linear term. So there's no term in X and del. There's only terms quadratic in X's and del's and a constant term. You could certainly add the linear terms here. It would just make the formula that I'm going to write down more complicated. So I'm not doing that. Basically, if you add the linear terms, you would get half integer g's, as was mentioned yesterday in the questions. Here we only get integer g's, integer genus with these terms, but not so important. So this is very general. So A, B, C, D here are general tensors, just basically a bunch of numbers. Okay. So now what you want to impose is the following. So if you just look at general H's, then you're not going to get an Airy structure. But what you want to impose is that if you commute any two of those, you get a linear combination of the other one. Okay, so F, A, B, C are structure constants. So in other words, what this means is that the H's are representations of a Lie algebra. That's what you're imposing in this case. Now you have to be careful here. So I could write this down. This, what you're imposing here is that this is a representation of a Lie algebra. So it doesn't have to be Virezo anymore, but it's a Lie algebra. Now, this is only because we're looking with degree 2 operators. If you want to go to higher degree, we don't have to impose that it's a Lie algebra. So I'll mention that in a second. But if you're working with degree 2 operators, then the F's have to be constant. So in other words, numbers. So you basically end up with the representation of a Lie algebra. But the point is that if you impose that, so these are just numbers, say in complex numbers, if you're working over complex numbers, if you impose that, then it's easy to show that you get the condition that you want on the left ideal. So this is, again, a good exercise. To prove that, it's only 2 lines to prove this. So if you write anything in the ideal generated by the H's and the H's satisfy these commutation relations, then the ideal also does satisfy this commutation property. Okay, so then of course that implies the usual statement, there exists a unique Z such that it is killed by the ideal here, because this is an Airy ideal. But now I'm going to write down explicitly what the recursion relation resulting from this is, because that will be our first encounter with topological recursion. Okay, so now if you, this is also a very good exercise, so I'll put that as an exercise. Basically, every calculation is a good exercise because I don't want to do them, so it's good. If you act with differential operators on Z, and then you end up with something that has to be 0, but these are formal sums in H bar and the variables. So if the formal sum, infinite sum, is 0, the coefficients have to be 0. So you end up with recursion relations for the coefficients. And what you end up with is precisely the following recursion relation. So on the one side, you have FGNs for any choice of indices K1, Kn in your index set. On the right side, you're going to get a whole bunch of terms. So the first term, so I'm going to write them down here. So it will take me a while, but it's important to write some formula. So the first term will be something like this. Get an A here, K2 to Kn. So here I'm not, when I have repeated indices like A here, again, I'm assuming that is sum over. So I should write this down here. Repeated indices are summed over in this slide. Oh, sorry, I forgot something. So you have to remove Km here. So I'm going to use a notation where the hat means the standard notation that I remove this index, this entry here. And then you get another term, which is the more interesting one, which is C, K, A, B. 2 types of terms. I get F, G minus 1, N plus 2. N plus 1, I think. A, B, K2 to Kn. And then I have a sum over all G1 and G2 that add up to G, and all subsets of K2 to Kn, disjoint subsets such that the union is equal to the set here. And I have a product of 2 Fs. I have an A, I, and the B and the J. Whew, we made it. Okay, so yeah, which is the first index of the tens? Oh yeah, sorry, that's a K1. Very good. That's not a K. K is not an index that appear anywhere. This is K1. AB. Thank you. And so this is a recursion relation. So this is a recursion on 2G minus 2 plus N, which was the degree, the power of H bar in the partition function. So that is completely recursive. And there's initial conditions. The initial conditions that you get, again, from the application of the differential operators, is that F03 ABC is fixed by the tensor A, and F11 is fixed by the tensor D. Okay, so altogether, this is completely equivalent to requiring that Z is killed by the operator H, the HAs. Okay, so this is a good calculation. This is not a two-line calculation, not like the other ones. This is, but if you want to get familiar with topological recursion, Airy structures, this is one of the calculations I ask all my students to do at some point, or I should ask all my students to do at some point. So it's basically just a formal manipulations of differential equations, but it is great. And you see this coming out, and this recursive structure here, this thing here is something that we will see over and over again in these lectures. This is basically one can think of that as one formulation of topological recursion. Okay. And it is just the action of the most general differential operators in h bar square, so degree 2 in h bar, that kills the partial function. Okay, now here's a question. So if you look at, just take that recursion relation. So take this recursion relation that I wrote down here. So you have initial conditions here. So this corresponds to the 2g minus 2 plus n is equal to 1. These are the two cases, and then this is recursive on 2g minus 2 plus n. So it seems that if you take any a, b, c, d, any tensor a, b, c, d, the recursion construct FGNs. So the question is, doesn't this always construct a Z? Right? If I give you any A, B, C, D, it seems like you just plug them in this recursion relation and you get a Z. Now, that would be very strange, because what it would mean is that for any choice of A, B, C, D, there is a solution to the constraints H, A, Z equals to 0. Right? So it would mean that, in fact, this condition was not necessary, because certainly for an arbitrary choice of A, B, C, D, this will not be true. It won't be a representation of a Lie algebra. So this will not be true. So what's going on here? Right? It seems to contradict everything we've done so far. Now, if we were in person, I would actually I would wait for someone to answer or propose an answer, but now we're virtual. So maybe I will not. But it is a very good question, and it's not obvious. The key here is symmetry. So the key is that, and that would take me longer to explain, so I'll just be quick here, but if you're interested, again, the lecture notes have more detail here. The key is if you look at this recursive structure here, it is not symmetric. Like, it's not symmetric under permutations of the entries of the FGN, right? The first entries are treated very differently from the other one. It's certainly all symmetric under permutations of K2 to Kn, but the first entries are weird, right? And to construct a partition function, you certainly want these to be symmetric under permutations of these, of all k's, including k1. And that is a very non-trivial statement. And it turns out that imposing that this recursion relation produces symmetric FGN gives conditions on A, B, C, D, and these conditions are precisely equivalent to the conditions required here so that the HAs form a representation of a Lie algebra. So that's a very non-trivial. This is a fairly complicated calculation. So this was done in this ABCO paper I mentioned before, and in this very explicit way, and it's a few pages long. So it's not an obvious calculation at all. But you can prove that this is true here. So everything is consistent. If you pick arbitrary ABCD, certainly you can plug them in here, but you'll get FGNs that are not symmetric, and then of course this whole thing is pretty much meaningless. So it doesn't construct anything interesting. Okay, so to get a symmetric answer here, you need this condition, which is key to the whole construction. Great. So so that's the example, the general example that gives topological recursion, as we'll see. But I should point out that there are many, many more examples that have been studied. So as I've said, all the examples so far that I've discussed were at most degree 2 in H bar. So that's very constraining, very restrictive. So we will see some later. So we will see more examples later. In fact, maybe we won't. I don't know. But one class of examples that is very interesting in that usually most of them involve operators that are higher degree in H bar is the construction of Airy ideals as representations of W algebras. So W algebras, if you don't know what these are, you can think of them as extended symmetry algebras of 2D CFTs. So remember that the Virazo algebra is the symmetry, the general symmetry algebra of a two-dimensional conformal field theory, but the conformal field theory might have more symmetries, might be have more symmetries. In this case, these are called W algebras, so they all include the Virazo algebra as a subalgebra, but they're bigger algebras. And you can construct a lot of examples of Airy structures as representations of those. In fact, we did a bunch, and I have a few papers that discuss this, and other people too. One example is if you take W algebras of GLR. If you don't know what this means, that's fine. At self-dual level, so this is a choice of central charge. But if you look with those, you'll get basically very nice result. You'll get that the constraints that you get are a natural Harry generalization of the Kontsevich-Witten and BGW constraints. And we'll talk more about this a little bit later when we talk about topological recursion, but you can get a nice integrability result and nice geometric result as well in this case. And one thing to note is W algebras are not generally Lie algebras, so this goes beyond just looking at representations of Lie algebras. So a question in the chat, what do we mean that the FGNs are symmetric because of what we imposed? So yeah, so I did not make it clear before probably, but when we have an Airy structure, an Airy ideal I, so Z, the partition function. So if you remember my definition of partition function, this was the exponential of a series in H bar whose coefficients were polynomial in X. So the coefficients, FGNs of these polynomials are always symmetric under permutations because these are polynomial in the X's. So the X's commute. So you can just permute the K's in the FGNs and you get something symmetric. So when we get a solution Z of the Airy ideals, the FGNs are always symmetric. Now the point here is that once we extract the recursion relations, we use symmetry if you do this exercise here of getting the recursion relations from the differential constraints, you will use symmetry of the FGNs. This is necessary to get this form here of the recursion relations. So you use symmetries of the FGNs, but the question is, if you now start with the recursion relations, so forget about Airy structures, start with the recursion relations here for arbitrary ABCD, this will not produce symmetric things because it treats the indices very differently here. So to produce symmetric FGNs, B, C, and A, and D have to satisfy very specific constraints, which turned out to be equivalent to these constraints. But this is highly non-trivial. You can't just see that by looking at the formula. What you can see is that it's not clear at all that this produces symmetric FGNs. Okay, so that basically ends my chapter 2, section 2 of these lectures, which is about Airy structures. And now we're going to move on to topological recursion. So that's a perfect time to take a 5-minute break. And now we're going to shift gears completely and go to the original definition of topological recursion from Hénard and Arantin. And then next, after we've done that and see a whole bunch of examples, then we'll connect the two and we'll see that they are actually the same, or rather, Airy structures is a generalization of the Hénard-Arantin topological recursion. So another question is that this is exactly the one used for Hurwitz numbers with cut and join. So that this recursion relation, or rather, well, yeah, you can write cut and join in many ways, but that this is the same. So the answer is not quite. It is not quite the same as the cut and join equation. However, it is very similar indeed, as you realize. It has very similar combinatorial structure, and in fact, Hurwitz numbers are an example of many types of Hurwitz numbers, and very large classes of Hurwitz numbers are examples indeed of topological recursion. And the way you prove that is indeed to go through cut-and-join equation. So I mean, by now there's many ways of proving that, but the simplest, more calculational way of proving it, proving that topological recursion provides generating functions of Hurwitz numbers, is to go through the cut-and-join equation, satisfy Hurwitz numbers, and show that it is indeed equivalent to this recursion relations. But it is not exactly the same directly. You have to do quite a few manipulations to relate the two. Good. Great. So welcome back. We are now, as I said, going to switch gears. Oh, am I still here? Yes. Looks like my video is frozen on my side.
No, it's okay.
Okay, good. I don't know why it's frozen on me. I can see myself with like a weird face. But okay. So yeah, we are switching gears and gonna start topological recursion from scratch, starting with the definition from Einar and Arantin's original paper in 2007. Okay, so this is kind of completely different. So now the point of view here is, again, it's a recursive structure, but now we're not talking about differential operators. We're not talking about partition functions. What we're talking about is the starting point is an object that we will call a spectral curve. And then we basically just are given a formula, which is this magic black box that we call topological recursion, and outputs this magic black box is a formula, a recursive formula that outputs a sequence of a collection of objects that I will call a system of differentials on the spectral curve, a system of correlators, sorry, on the spectral curve. Okay, and as I've pointed out, I introduced you to these in the very introduction when I talked about Witten's conjecture. So these are another way of, at least that's the idea, of forming generating series for nice numbers FGNs. Okay, but what we want to do now is define the notion of spectral curve and define this black box called topological recursion. By the way, the name topological recursion was not used by Einar and Arantin. Obviously, they just talked about a recursive formula. I think it came later. I think it was introduced in some paper of Motohiko Mulazi at some point, I think. And then it has become standard to use that name to denote that particular recursion. But of course, topological recursion might mean other things in different contexts because there are many recursive structures that are topological in some way or another. So, but what I refer to here is this particular recursive structure. Okay, so what I'm going to do is first define the notion of a spectral curve, and then we'll talk about the recursive structure. So what is a spectral curve for us? Okay, so definition, a spectral curve is what? It's basically four different things. So it's a quadruple. So let's call S the four things. So C, X, omega 01, omega 02. And then I need to define these things. So what are those? Okay, so sorry, I wrote C, but I want to use sigma, otherwise I'll be confused with my notes. Sigma here is what? So it's going to be a Riemann surface. Now, before I even keep going, what I should say is that if you look at the literature on topological recursion, as I said, there's been like hundreds of papers since it came out. Spectral curves are defined differently. There are many different definitions of spectral curves, some more general than others, some trying to be more precise. The definition I'm using here is not the most general one, but it's good enough for these lectures, but it could be generalized. Sigma here for us is going to be a Riemann surface, but I don't necessarily assume that it's a compact. So sometimes Riemann surfaces are defined to be compact. So here I don't necessarily assume that it's compact, but in many cases it will be, but it's not necessary for us. X is going to be a holomorphic map between Riemann surfaces, so you can think of it as a branch covering. So it's a holomorphic map between sigma and P1. Omega 01 is going to be a meromorphic one form on this Riemann surface sigma. Okay, so far so good. And then the last object here in the definition, omega 02, is a little bit more mysterious. So what it is what's called a fundamental bidifferential. So if you are fine, what I would suggest is that I just don't talk about omega 02 for now, and I'll come back to it in maybe half an hour. Because it requires a little bit more care to define what it actually is. Okay, but it's basically a fundamental bidifferential. It's been called Bergman kernel too. It's been called canonical bilinear differential. Lots of different names. It's something that was studied classically in the geometry of Riemann surfaces, but somehow was hidden or like studied in some book of Fay and Farka, I think, but was not necessarily well, no. Okay, but I'll define that in a second. Okay, so that is what we call a spectral curve. So it's four things. You start with a Riemann surface, you have a map or a branch covering between two Riemann surfaces, you have a meromorphic one form on this Riemann surface, and a fundamental bidifferential. Now, one thing I want to remark before we look at expand on that geometry, one thing I want to remark is that it's some simple geometry. If you have a holomorphic map between Riemann surfaces or between sigma and P1, this is completely equivalent to specifying a meromorphic function on the Riemann surface. So you can think of X as a meromorphic function on sigma if you want, or as a holomorphic map. It's completely equivalent, just two different points of view on the same thing. And similarly, if you have a meromorphic one form and you are given a meromorphic function X, you can write your meromorphic one form as y dx, where y is another meromorphic function on your Riemann surface. So what this means here is that instead of defining X as a holomorphic map and omega 01 as a one form, I could have defined spectral curve as being a Riemann surface, two choices of meromorphic functions, X and Y, and a bilinear differential, a fundamental bidifferential, which is how it's defined in many of the papers, but it's equivalent to how it's defined here. Okay, I really don't know why my camera is frozen on my screen. But, oh, it's not anymore. Okay, good. But now oops. Sorry, I'm just trying to figure out Zoom a little bit now. Oh, hi meeting, that's what I want. Okay, good. Well, now I don't see myself at all. Okay, that's even better. Great, so where do we go from there? So this is the spectral curve. So now let's explore the geometry of the spectral curve a little more so that we can formulate topological recursion. So let me look at the case, special case, where sigma is a compact Riemann surface. As I've said, I don't need to assume that, and in fact, I will not need to assume that in anything I say from now on. But I just want to highlight the geometry in this case because things are nice. So if sigma is a compact Riemann surface, then this map here, this is well known in geometry, has to be a finite degree branch covering. Right, so this is a map of finite degree. So the pre-image is a finite number d, say, of pre-images for a given point in P1, and it's branched, meaning that for some points in P1, the number of pre-images might be less than d, which correspond to the branch points in P1. If sigma was not compact, X could be infinite degree. So that's why we have to be careful. But we're gonna assume that X is finite degree here, and that's true if sigma is compact. Another fact that is true if sigma is a compact Riemann surface is that there always exists an irreducible polynomial P such that polynomial in two variables, such that if you're given any two meromorphic functions, independent meromorphic functions on the Riemann surface, then they satisfy a polynomial equation. So what this means is that you can think of sigma, the Riemann surface, as the normalization of this affine curve, of this plane curve. So again, that's another way of thinking about Riemann surfaces. Here is that you can think of, okay, I'm back. You can think of this Riemann surface as a plane curves, right? A spectral curves, sorry. Another way of thinking about spectral curves is that you can think of spectral curves as basically plane curves, which is how it's introduced in some papers. And that's relevant. You have to think of it if you want to connect with quantum curves and WKB analysis and all these things. So that might come back later. But this is only for a very special case. There's a lot of spectral curves that arise that are interesting, that are not coming from plane curves. They might involve exponentials and stuff like this. Okay. Okay, but now let's explore that geometry a little bit more. So X is a finite degree covering. So what does that mean? So it means that if you pick any point P on your Riemann surface, then locally near this point and near the image of this point in P1, you can always write your map as a very simple power map. Right? This is called the local normal form of the holomorphic map. And what it means is just that locally, you can always think of your map as just being a power map. So in other words, it just takes all the pre-images and map them to the point in P1. Okay, this is very general. If you think of X not as a holomorphic map, but as a meromorphic function, then the equivalent statement is that you can find a local coordinate zeta here such that locally you can always write your meromorphic function as x of p plus zeta to the r if x of p is not infinity in your choice of coordinate x on P1. If it is infinity, so in other words, if you think of x as a meromorphic function, you've basically fixed the coordinate in P1 and if you think of it as a holomorphic map. But now we think of it as a meromorphic function. So if the point P is not a pole of x, then you can write it like this. If it is a pole of x, then you can write x zeta as 1 over zeta to the r. Okay, so that's a very general statement for any meromorphic function. At a point P, you can either write it like this locally, so there's a choice of local coordinates where you can write this, or like this. That's just a local a local statement, right? This is not a global choice of coordinates on your Riemann surface. Okay, but that's very important for us because now we can define ramification points and ramification order, which will play a very special role in the definition of topological recursion. Okay, so given a point P, this integer r here, so we could write rp everywhere just to specify that this is at the point P. So this integer here, rp, is called the ramification order of the map. At the point P. Right? Clearly you see that if r is equal to 1 or minus 1, then the map is 1 to 1, right? So it basically maps neighborhood to neighborhood. But if r is greater than 1, then the map is not 1 to 1 anymore. So the point is ramified here. So that's exactly how we define ramification point. So we say that the point P here is a ramification point of the map if rp is greater or equal to 2. Right. So actually r is not minus 1. Sorry, the way I've defined it, r is always positive. Of course, it's a positive integer. Okay, so and these these ramification points are easy to find. So these are basically at zeros of the differential of the map dx, or the differential of the meromorphic function, and the poles, if you think of x as a meromorphic function, the poles of x of order greater or equal to 2. Okay, so that's basically very easy to find. You find the zeros of the differential of the function x, and you find the poles of x of order greater or equal to 2, and that gives you all the ramification points of the holomorphic. So question in the chat, in this case, sigma is defined by P of xy and inside and C2. So yeah, so here, this is, I guess that refers to here, this is a plane curve in C2. So of course, a plane curve defines a non-compact Riemann surface, but then you can find the normalization of that Riemann surfaces, which is basically compactifying the Riemann surface, and sigma would be the normalization of this Riemann surface. So it would be the compact Riemann surface you get in this way. Okay, so, and then this is just notation. So I'm going to write RAM for the set of ramification points of the map X. And this will be very important for the definition of topological recursion. So one way to think of ramification points, very pictorial way, is the following. So you have a map X, right? So this is P1, and then you have sigma here, and this is a finite degree branch covering. So for a given point, you'll get many pre-images. So you can think of the map. I mean, this is of course schematic because everything is complex here, and I'm just drawing lines. But basically, what you mean is that given the point here, you have a bunch of pre-images. So that would be an example of a degree 5 map. So you have 5 pre-images generically. But it might happen that somewhere you get less than 5 pre-images. So you could get 2 sheets, something like this, that meet here. So at this particular point here, you get exactly 4 pre-images, right? So that would be, this point in the base would be what's called a branch point. And the points here where the 2 sheets meet would be called a ramification point. Okay, so this point here is the ramification point. This point here is the branch point. And if you think of that, near this point, the map is locally just a 1-to-1 map, just the identity. But near this point, the map locally is a 2-to-1 map. So this is a power map with R equals to 2 here locally. Okay, and so these are the ramification points. So that's one way to think about them pictorially. Okay, so great. We know about ramification points. So this is going to be very important. So I have to keep this in mind. What else do we need? So what about omega 0,1? So what do we need to know about omega 0,1? So far we've talked about sigma, the Riemann surface, x, the branch covering. What about omega 0,1? Well, okay, so you can also expand your one form in the local coordinates. So suppose that you're given the local coordinate zeta that I had before at a point. So this is the coordinate such that the map takes the local normal form. Then you can write down an expansion for your meromorphic one form. And that's just the standard Laurent expansion. So it will start somewhere. I'm going to call that S bar. Some coefficient here, tau k, whatever they are. And then you have zeta k minus 1 d zeta. So it's just a choice of way of expanding here, way of writing my expansion, but this is just the standard Laurent expansion of the one form near the point. Okay. Great. So now I'm also going to define another integer here. So this defines an integer, of course, S bar, which is the basically the smallest power zeta that appears in this Laurent expansion, and or S bar minus 1 would be. And then I'm going to define S to be very similar. So formally, it's defined as the minimum of all the integers here, k, such that tau k is not equal to 0. So if I stopped here, then S would be exactly equal to S bar. But now we want to look at such thing where R does not divide. Okay. So in other words, if the smallest power, smallest the S bar here, the smallest power, so that tau k is not 0, is actually a multiple of R, we go to the next one. Right? So we want to look at the first, I mean, the reason is not obvious at all, but when we formulate topological recursion, these things are a multiple of R disappear. So they don't really matter. But what matters is the first power that will not be divisible by R. And that's what we call S. And with these things, we can define local data. So the local data of a spectral curve, of these spectral curves, sorry, at a point is basically given by these three integers. So it's given by the ramification order at that point of the holomorphic map X, S, the integer S bar, which is the smallest power of zeta, appearing in the expansion of the one form, and the integer S, which is the smallest power of zeta, appearing in the expansion that is not divisible by R. Okay, the reason we need that is because topological recursion will not be defined for arbitrary spectral curve. It's only defined if some condition is satisfied in the spectral curve, and that's actually very subtle. Now, in these lectures, I'll define that. Now I'm being quite rigorous here, defining everything carefully, but the examples we'll look at in this lectures are much simpler. So, but let's just define the general statement. So we need to restrict to a special class of spectral curve to define topological recursion. So if you take S to be a spectral curve, then we're going to say that it is admissible and that's what you need to define topological recursion at a point. Well, it will have to be admissible at every point. So we say that it's admissible at a point if either this is not a ramification point, so Rp is equal to 1, or let me just write R, avoid having too many indices, or R is a ramification point, and then we need three conditions to be satisfied. So R and S have to be co-prime. Second, either S is less than or equal to -1. This case is actually not interesting because it doesn't contribute to topological recursion, so we're mostly going to forget about it. Or S is between 1 and R plus 1. And very weird condition, R is equal to plus or -1 mod S. So some sort of modularity condition here. And the last one is not so deep, but to be rigorous, we need to state it. Either S bar is the same as S, or is one less, or one more. Okay. All right, so that's a lot of definitions. And what we'll do next is look at examples, so that will make this clear. But the point here is that if these conditions are not satisfied, topological recursion is not well defined. Now, this is something that NR and Alberta did not realize because they were looking at a very special case, which is what we're mostly going to focus on these lectures, where all points, ramification points, are at most of order 2. So where R is either 1 or 2. So it's either not ramified or simple, what we call simple ramification points, only order 2. If you do that, then these conditions of admissibility are actually quite a bit simpler, as I'll explain. But if you want to do the general case, you need to impose that. And these conditions were only realized, only found in a paper I was a co-author of 2017, 2018 on W algebras. And the way we found them is using Airy structures. So actually, it's Airy structures provided a lot of these more rigorous constructions that were not clear from the point of view of topological recursion. Okay, all this to say that these are very non-trivial conditions, but they're necessary. So we'll have to impose that. But let me do a few examples of spectral curves before we talk about omega 02. Okay, so the first example is going to be called the Airy spectral curve. So again, Airy appears because it will be related to the Virasoro constraints that give Kontsevich-Witten and all these things. So it's the prototypical example. Okay, so this example, if you think of it in terms of quadruple, so sigma x omega 0, 1, omega 0, 2. What are those? Well, sigma will be just complex numbers. You could also take it to be P1 here. To be honest, it makes no difference. But let's just take the complex numbers. X is going to be the map z square, or 1/2 z square if you want. So this is now a degree 2 map, and it's globally defined as just the power map. Right? So that's a very special case. In general, the map is only locally defined to be a power map. But in this case, this is what you take. So there's only one ramification point here, which is at 0. And we're going to take omega 0, 1 here, the one form y dx, to be given by z square dz. So in other words, y is equal to z here. So a very simple meromorphic function. And again, I haven't talked about omega 0, 2 yet, but just for completeness, let me write it down. In this case, it would be this very simple object. Okay, so this defines what's called the Airy spectral curve. It's very simple. You can think of that as a plane curve here, right? Because if you think of x and y, so y is equal to z, x is equal to 1/2 of z squared. So if you write down this equation, then this is identically satisfied by x and y. So equivalently, you can think of x as y as a parametrization of this equation. So you can think of the Airy spectral curve as being given by this affine plane curve. Okay, so that's another way of thinking about it. Now, what is the ramification set here? So there's only one ramification point, which is at 0. So these are the zeros of dx. dx here is just z dz. So there's only a 0 at z equal to 0. And there's no pole on the map x if we work over C. So that's only one point. The local data at this point is simple. Well, r is equal to 2 because that's globally defined as a degree 2 map. S is equal to 3, which is also the same as S bar. S bar is equal to 3, right? Because it's the leading power of Z and omega 0, 1 is 3 minus 1. So that's 2. So that means that S is equal to 3. So R and S are co-prime and all the conditions. So basically this the admissibility conditions are satisfied. So that's admissible. And that's called an Airy spectral curve. In fact, we will say that any ramification point that locally looks like this, in other words, any ramification point that locally has the data r equals 2 and s equals 3, we'll say that this is locally Airy, because locally it just looks like this curve. Okay, so this is perhaps the simplest. Now, the second example I'll talk about is almost just as simple, but it was studied quite a bit later. So the Airy case was obviously studied in Alberta. That was the prototypical example they looked at. The second case, which we're going to call the Bessel spectral curve, was studied later by Norbury, Doe, and other people too. But it is also very similar. So if you think of it in the same way as a quadruple, so you still take the complex number, x is the same, so it's globally just the power map, and then you change your one form. So omega 0, 1, which is y dx, you take to be just dz. So that's the same as taking y to be 1 over z, right? So you see all I'm changing here, y is still a 1-to-1 map, so just a simple meromorphic function, but it's 1 over z instead of z. And that's all I'm changing. Take the same omega 0, 2 here. Now, again, you can think of that as a parametrization of a plane curve, but in this case, the plane curve would be this one. Okay, so that's easy to see. This is a parametrization. The choice of x and y are parametrization of this curve. And again, there's only one ramification point here because I haven't changed the map x, but the local data at this point has changed. So r is still equal to 2, but now s is equal to 1. And again, s bar is equal to s. And whenever this happens locally, we're going to call this as the ramification point of Bessel type. Okay. And that's cool. So if you look at points with r equals 2, so simple ramification points, these are the only two choices of S that are allowed by the admissibility condition. Okay, so if you go back to the admissibility condition I had here, if you unpack this complicated condition when r is equal to 2, you'll see that there's actually only two choices. Well, there's S less than or equal to -1, but we can forget about this, as I said, it's a technical reason. But the only other choices is S equals to 1 or S equals to 3. And S bar here, but again, S bar is not so important for the rest. So these are the two cases, and we call them Airy and Bessel. Okay, so we can state that as followed. So if you take a spectral curve such that all ramification points are simple, so r equals 2 at every of them, at all of them, then the admissibility condition that I pointed out before is equivalent to saying that these points are all locally Airy or Bessel. So locally, they look exactly like the two examples I had before. So again, this is assuming that we forget about this S negative case, which we can forget because these will not contribute to topological recursion for reasons we haven't seen yet. Okay, so these two things you can really think as the building blocks. These are the building blocks of all spectral curve with simple ramification. Okay, and in the original paper of Henard and Latam, all they looked at is spectral curves with simple ramification. So when they defined spectral curve, they imposed that all the ramification points are simple, so that you only have two sheets, r equals 2, meeting at these ramification points. So all their cases correspond to either Airy or Bessel locally. But of course, globally, things can be a lot more complicated. X could be a very complicated polynomial function, or it doesn't have to be polynomial even. It could be some very complicated function, but locally, it's always a degree 2 map. Okay, and then you could ask, so in these lectures, I'm also only going to focus on simple ramification, but I want to point out here and there how it generalizes to the general spectral curve, because there's a lot of really nice geometry in this case. So you could ask, what are the building blocks for the more general case? And these have been known as the RS spectral curves. So the general building blocks are similar. So you take same Riemann surface, but you now take X to be a power map, but of degree R. Right? So where R now is any positive integer greater or equal to 2, because 1 would be trivial. And now we're going to define omega 0,1 to be some one form that starts with some RS here. Now we're going to impose that S is between 1 and R plus 1, and that R is equal to plus or minus 1 mod S. And we take the same omega 0,2 as before. So these are fairly simple spectral curves. So they are called the RS spectral curves because of obvious reasons. They're determined in terms of two integers R and S. And these are the building blocks for general spectral curves. So what does it mean? It means that if I take a general spectral curve, then locally it looks like one of those. But of course, the global geometry might be much more complicated than this. But if you understand what's going on for these ones, you can hopefully understand what's going on in general terms. Okay, so these are cool, but I will mostly avoid talking about the general R case because the formula become very messy, and especially I'm writing everything here, so it would take me a lot of time writing all these general formula. So I will only point out how it generalizes and refer to the papers when needed. Okay, so this is basically the general idea of spectral curves. Now, the one piece that I have not talked about yet is omega 02. So I did write down omega 02 a number of times for these special curves, but I did not tell you really what omega 02 is. Okay, so I think I have time to actually do that, so that's perfect. So let me define omega 02 more carefully and tell you why it is important, because it will play a very important role in the rest. Okay, so let me first define what it is. So what is omega 02? So I said it's the fundamental bidifferential. So what is this? So omega 02 is a symmetric bidifferential. So what does it mean? So it means that it's, as you've seen in my example, it was dz1, dz2. So it's a bidifferential on two copies of the spectral curve, where there's only one pole whose only pole consists of a double pole on the diagonal. So if you write your coordinates as z1 and z2, like I did, this is a pole at z1 equals to z2, with what is called the bi-residue equal to 1. So what this means is the leading coefficient is 1. So in other words, what this means is that locally you can write it as something like this, plus holomorphic stuff. Or rather, I should put the dz's outside. Okay, but the holomorphic part might be complicated. Okay, so that's the definition of a fundamental bidifferential. Something that has only a double pole and diagonal and no residue, or and bi-residue equals to 1. I should have said no residue here, with no residue and bi-residue equals to 1. I guess that's clear from my leading order behavior. Okay, and then the easiest example, of course, is what I've used so far. So if you take your Riemann surface to be equal to C or P1, because it really is the same here. So then the natural choice is to just take this with no holomorphic part. I mean, if you're working on P1, this has to be the case. If you're on C, you could have potentially extra term here because you could have a pole at infinity, because infinity is not on C. But that's the one we usually take, right? So that would be the bidifferential here. Okay, and then another example, if you take sigma to be any compact Riemann surface, then one can show that there is actually a unique fundamental bidifferential if you impose a normalization. So this is the statement that if you integrate in one of the variable over a basis of cycles, so these are the A cycles, so you integrate over one of the two variables, and you impose that this is 0. So this A's here are basically a basis, symplectic basis. So let me call the genus of sigma G bar to distinguish between G that appears in topological recursion. So these would be a basis of cycles. This is a symplectic basis for H1 of your Riemann surface. So if you're given a symplectic basis, then you can normalize the differential over that basis, over the A cycles, and then it turns out to be uniquely defined. Now, this is not obvious, but this is how this object was defined classically in the literature on Riemann surfaces. And in this context, it has been called the Bergman kernel. So if you read papers on topological recursion, you will probably see these names, Bergman kernel. What it is just the fundamental bidifferential, but on a compact Riemann surface. So it is defined, it is uniquely defined once you choose a symplectic basis on that surface. But as far as topological recursion is concerned, you can be more general than that, because sigma doesn't have to be compact. I mean, if it's not compact, then there are many possible choices for the fundamental bidifferential. Okay, now in these lectures, all the examples I will do, this will always be the choice that we make, but you should not think that this is always the right choice. Sometimes you need to take different choices. But That's the one we'll use. Okay, and then the question is, of course, why do we need to specify that? So why do we need omega 02 to define topological recursion? So that's a good question. And it turns out that omega 02 has some very nice geometry. So I'm going to try to define that because we're going to use that to define topological recursion. Okay, so I think I have just enough time to go through that. So that's perfect. If that's okay. Everyone's still awake. Okay, so why do we need omega 02? So the point here is that it defines a projection. So pick any point on your Riemann surface, and then pick any meromorphic one form on the Riemann surface. We can define a projection as follows. So let me write this down. So we define a projection, I'm going to call it B hat, at the point P of the one form. And the way it's defined is you take the residue at this point of the integral of omega 02. Now you have to integrate locally near the residue, because if your Riemann surface is homogeneous, the integral might be ambiguous here, but you integrate locally. And then you take, sorry, that should be outside. You take the one form, take the residue, and that defines a projection. So what do we mean by projection? So the key here is the following lemma, which is, again, a few lines to prove that. The statement here is that this new object that we just constructed is also a meromorphic one form. And it has the same principal part at the point. Okay, the principal part is if you do a Laurent expansion, and at the point you keep only the terms with negative powers. In your Laurent expansion, that's called the principal part or the polar part. And then B hat P alpha is a different one form, globally on sigma, but it has the same principal part. Now, the way to prove that is fairly easy. What you do is just expand in local coordinates. You take a local coordinate at P, you just expand, and you'll see that this is true. And also, it is a projection, meaning that if you project twice, you get the same thing, right? So if you add twice, so if you define the new one form, B hat P of alpha, and then you do it again, you'll get the same thing again. So it gives the same one. Okay, so this is very cool, because why is it very cool? So you can think of B hat as what I would call a local to global operation. So in what sense? So if you want the input, what I call alpha above, I said alpha is a meromorphic one form on sigma. Okay, but you actually don't even need that. You could only start with the local data, or the germ if you want, the local data of a one form at P. Right, so you can only write down the expansion, right? You just write down an expansion. You just start with the local data of a one form at P, and what the operation, the projection here does, is that it produces a globally defined one form with the same principal part. Okay, so that's kind of cool, right? So it starts with some local data and produces something globally defined on the Riemann surface. So that's very cool. And this is why it is important, because how you do that is not unique, right? Because of course, when you produce this globally defined one form, if you add anything holomorphic, you still will have the same principal part at the point, right? If you add anything that's holomorphic at that point, it will not change the principal part. So how you go from local data to global is not unique, and that's exactly where the choice of omega 02 come in. So which way you do that is specified by omega 02. So this is the choice of omega 02. So you can think of omega 02 as being some data that tells you how to construct globally defined object out of the data of local data at points on your Riemann surface. Okay, so this is the projection, and this is something we're going to use a lot in topological recursion. So actually, I think that's even better. I can finish with my last slide. So using this projection, we can define a bunch of things, and then we will be ready to start the lecture on Monday with topological recursion. So using this projection, we can first define a basis, a natural basis of one form at any point. So pick a point on your Riemann surface, P, then you can define a choice of basis. So what do I mean here? So you're going to pick your point, take any integer k. Let's do it for natural numbers. Pick a local coordinate. Then you can define a one form, xi, the point P. Well, this is a globally defined one form, but it's specified by the data at P. And you define that as being the projection of the natural one form that has a pole of order k plus 1. So you basically want to define a basis of one forms that have poles at the point of higher and higher order, and no other terms in the Laurent expansion, negative terms in the Laurent expansion. So in local coordinates, these would be just the powers of zeta in the local coordinate, but you want them to be globally defined. So you can't just write d zeta over zeta k plus 1 because that's just local. But you act with your projection, and then you get something that is globally defined that has the same principal part. So in the local coordinate, it would look like this. But now holomorphic is specified such that these are globally defined object on sigma, right? So these are one forms on sigma that basically have poles of order k plus 1. Sorry, at the point you start with P. Okay, so this is a natural basis which will be which will appear in topological recursion. And then you can say, you can prove that if you take any homomorphic one form, alpha, on your Riemann surface, and you project it, the x's are a very nice basis because you can now write this as a finite sum. So I'm going to write it as a sum over positive integer, but there's only a finite number of non-zero coefficients in terms of that basis. There's only a finite number that are non-zero. And that's why we call that a basis. So you can think of it as a basis for expanding these one forms that are projections, the projection of these one forms at a point, right? So that gives you, if you were, so the point here, maybe it's not clear, but if you were just expanding in zeta, then of course the expansion here would be a Laurent expansion. So you would have a finite number of negative terms, or you get an infinite series in the positive direction. But once you write it in terms of that basis, then this is a finite sum, right? So that's very important, and that leads us to the last definition I'm going to say today, which is what we call the projection property. So we say that any one form alpha satisfies what is called the projection property if it's equal to its projection. So that's at a point. If the projection of the one form is equal to the one form, right? So that's definition. And of course, there's some nice direct implication, which is that there's alpha has an finite expansion in the basis that I just defined. And this will be key to connect topological recursion to Airy structures. Okay, so all of this is a lot of, this is probably a lot to digest. run these lectures, but it's very nice geometry. What you should get out of these last 2 or 3 slides is that the choice of omega 02 here corresponds to a way of constructing globally defined object out of local data at points. And once you've chosen omega 02 or a projection operator, you have a natural basis, which are these x's, so that the projection of any one form or any one form that satisfies the projection property has a finite expansion in this xc basis. Okay, so that's the key of omega 02, omega 01, x, and sigma we've already seen. These define basically the geometry of the spectral curve. So I think that's going to be it for today. And then what we're going to talk about on Monday is now topological recursion. So now we have all the geometry set up. We just need to write down what the recursive formula is and look at many examples of how wonderful this recursive formula is. Okay, so thank you very much. And yeah, if you have any questions, I'm still here. And there is one right now in the chat. So the question here is going back to omega 01, is there some sort of after the fact interpretation of condition 2 in terms of something topological? Some type of local descending condition on omega 01 from sigma to P1. So condition 2, what do you mean by condition 2? Going to, condition 2 in the immiscibility? Oh, this condition here? Oh, yeah, okay. So is there some sort of interpretation of condition 2 in terms of something topological? So this condition, R equals plus or minus 1 by S, so I should say a few words about that, because that's a very interesting, there's an interesting history, kind of. So this condition here is very mysterious, to be honest. We found that in a paper, as I said, in 2018, when we studied W algebras and Airy structures. And what we did not expect that at all. We expected that it would work for, I mean, the coprime condition is obvious from the formula, from topological recursion. This condition is very mysterious. So we did not expect that at all. And we were trying to prove that topological recursion is equivalent to these W algebra Airy structures we constructed. And then along the way, we realized that the Airy structures only make sense when this condition is satisfied, because otherwise the conditions of Airy structures are not there. So the first condition that the operators have the right form, and in fact, both of them together imply that this must be true. So we were really surprised. So we were thinking, okay, probably something wrong in there. But then we looked at topological recursion and realized that indeed, if this is not satisfied, the recursive formula that I'm going to talk about later does not produce symmetric correlators, which was a surprise to us, and no one had noticed that before. Just because no one thought about it. So everyone expected that it would produce symmetric correlators, but it hadn't been proved. So a lot of things in topological recursion, by the way, it has an interesting history, because you know, a lot of things are done by physicists, so not always fully rigorous. So many statements are kind of stated and then only proved later, and then realize, okay, maybe it's slightly different than what was stated. So it's not always obvious to know what is actually true or not. But the point here is that we realized that this had to be true, and it's certainly true now that this has to be true. But it's still mysterious, so it's not clear why. I mean, it's clear from the formula why this has to be true, as I said, because otherwise it doesn't produce symmetric correlators. But it's not clear what the geometry is here. So why, you know, from the definition of spectral curve, why should you have this condition? Is very mysterious, and even in, you know, relations with integrability or in immersive geometry. So as I'll mention later, these cases are still very mysterious for this. In fact, we're writing a paper on this right now. But this modularity condition is very mysterious. And there's a new paper, a new series of papers of Shadrin and others from last year, where they define a different topological recursion for the cases where R is greater than 2. Where this condition is not required anymore. But it is a different definition. In fact, it's not really a recursion in this sense. It's defined using what's called symplectic duality and relation with KP integrable systems. It's very cool. What they do is really, really cool, but it's different. And in that context, they don't have this condition. But yeah, but if you just do topological recursion, you would have this, and it's still fairly mysterious.